So I defined UQ of GA. So this was the quantum affine algebra. And it has Chevalier generators and relations, so I'm not writing those again, I've written them before. Okay. And more importantly, it has an alternate presentation. And these are, so it's a loop-like presentation. This was given by Drinfeld. So you have infinitely many generators, XIR plus or minus, one for each simple root, one for each integer. You also have another collection of generators, which is HIR, same range, but this time we insist that R is not 0, and KI plus or minus 1. And they satisfy a million unilluminating relationships, so I won't write them. But let me isolate for you what the important points are. So one is that so the elements HIR, and I want to also say that this quantum affine algebra, so UQG hat, has a canonical central element. Okay, just like the affine Lie algebra had a canonical central element, the quantum loop algebra also has a canonical central element, and which is actually a product of k's. And so what you do is that you and since the k's are invertible, the quantum loop algebra is the quotient. So UQ of LG. So let me call this canonical central element capital C. And so UQ of LG is UQ of our affine algebra modulo C minus 1. So you get rid of the center. So for the affine Lie algebra, you have to take C minus C to quotient out. So it's actually C equals to 0. But here you have to, since H's get replaced by K's and K's are invertible, you can't put it equal to 0, you put it equal to 1.
The D is not part of the qualification.
Yeah, we take the derived thing here, we won't have D's in it. Or, so, I mean, Kashiwara, for instance, would call this UQ prime, because he would get rid of it. I don't want a derivation for this one. But you can put, otherwise if you want the derivation, then you quotient different by G as well. Okay, so what we're interested in, so as before, finite dimensional representations of UQ of the affine algebra are the same as finite dimensional representations of the loop algebra, so of UQL. Okay, so I should have set this. And now let's go back to here. So this loop-like presentation, I have these elements XIR plus or minus HIR, which satisfy many relations. And the two things that I want to isolate are the following. So the relevant relations for what I need to say is really that the elements HIR commute in UQ of LG. So you have a nice infinite dimensional Cartan subalgebra, just like you did for the loop algebra. And because they commute, You can also define these garland-like elements, which I defined yesterday, and you have to put in certain, so this will be summation r greater than or equal to 0, PIR u to ER. This will be equal to exponential minus summation HIR u to ER, r greater than or equal to 1. And you divide, now in Garland's formula, you divide it by r, right? So here you divide by quantum r. So this is the modification that you need. And then you have exactly the same result. So then the theorem, so I should say that then I should make some more comments because these comments are all relevant to what makes life difficult. So, comment. Now, so when I wrote down the Kac-Moody algebra, U cubed GA, when I wrote it down in terms of Chevalier generators and relations, I gave you explicit formulae for the co-multiplication, right? It was something like EI, or it was XI plus tensor K plus 1 tensor XI plus, and so on, and we discussed how this was not co-commutative and things like that. Now, when you go to this presentation, what makes life really unpleasant is that you don't know, so no explicit formulae are known for the co-multiplication on the elements XIR plus or minus and HIR. Okay. So this in the SL2 case there is one does know things, so except in SL2. This was done in somebody's thesis. I forget his name now. He was a Finnish guy. So except for SL2. So this was the thesis from Uppsala University. And somebody's thesis, I don't remember the name. But knowing it for SL2 is not enough. Usually you think if you know the co-multiplication for SL2, you can just expand it. But it isn't. It depends drastically on the Lie algebra. And so it's just no good. So one doesn't know explicit formula. What one does know, so one just has some information on the first order terms. And so whenever you're trying to take tensor products and working with these loop generators, you somehow have to get all information by just knowing this much. You don't have the full force of the thing. And that is one of the difficulties in working in this area. It's much nicer to be classical. So let me tell you, so again, this is another point. So let me tell you what co-multiplication looks like on these elements. Okay? So this is a power series. Let me give this power series a name, so I'll call it.
So if you have the other presentation, then the co-multiplication is.
Because this is just Chevalier generators. So it's just the usual formula. But these generators aren't usually enough when you're doing finite dimensional multiplication. So let's call this thing PIU. So if you remember, I made this comment that this is a well-known equation in the theory of symmetric functions relating power series, power sums to complete symmetric functions. Okay? The other thing one knows about the ring of symmetric functions is that it is off-off. It comes equipped with a canonical co-multiplication. Yeah, and so this you could ask what is the multiplication on this. And this actually reflects the co-multiplication on the ring of symmetric functions. And so if you think about it for a bit, it looks like PI, the co-multiplication there. This element behaves like a group-like element. So it'll look like this.
Excuse me.
Yeah.
Are these PIs inside of the quantum loop algebra or the quantum? Are they inside UQLG or UQG hat?
These can live in either place the way they're defined.
But the H's are not going to be. You're going to have trouble with this exponential sum in the UQG hat case because it's not commutative anymore.
But r greater than or equal to 1. Is r greater than or equal to 1. So what does the relation look like? It looks like h tensor t power n commuting with h tensor t power m, right? So it'll be 0 plus n delta n minus m times the killing form.
Okay. Somehow that doesn't.
So the point is that these elements are commutative. HIR commutes with HIS if R and S are both positive. So you can do this in either place. So yeah. So what does this co-multiplication mean? They're written in this way. It means that plus correction terms, which we'll never worry about the correction terms, we'll always assume that we can manage things. So what does this mean explicitly? So this is a very nice way to write the formula. What does it mean explicitly? It means that if you calculate delta of PIR, that's equal to summation S equal to 0 to R, PIS, tensor PIR minus S, plus things that I don't care about. So this appearance of these symmetric functions in here is something very mysterious. And the fact that it comes with the co-multiplication as well is something that sort of people don't understand. And I think it's only after we found. So this is something that we did with, so part of this was joint work with Presley, and the other part of it was joint work with Beck as well. Okay. Okay, so okay, so this is something that we will see. How does this get used? So again, if you're working in the classical situation, remember, then I just replaced this by the integer r rather than the quantum integer. Then there's no correction term. And so this just says that this is exactly a group-like element in my enveloping algebra. And how does this reflect itself in representation theory? So let me just tell you what it did for U of LG. I didn't say this yesterday. But supposing I had my irreducible representations, which I want to parameterize by the Drinfeld polynomials. I don't want to think of it as linear finitely supported functions. I want to think of it in terms of. So if I look at V pi tensor V pi prime, right, we know when this tensor product is irreducible. It is a tensor product of evaluation representations. We know when it's irreducible. What that formula tells us is that this is isomorphic. So you see the p's act as scalars on the highest weight vector here. They act as scalars on the highest weight vector here. It's reasonable to ask, how do they act in the tensor product of the highest weight vectors? Right? If you're doing simple algebras, it's just lambda plus mu. Over here, what that formula is telling us is that they act as the product. If this acts irreducible. If this is irreducible, then what is it? So there are conditions where this is irreducible, then you want to know what the Drinfeld polynomials are, and they just multiply up. And the way that's proved is using this formula. And that remains true in the course. Okay. So then the theorem that we proved in 90 and 94, no, yeah, I guess 90 and 94, is that the irreducible finite dimensional representations of UQLG are given by Drinfeld polynomials. So by given by an n-tuple of polynomials with constant term 1. In fact, so I want to make a statement, because, and then I'll tell you why I'm making a fuss about this. So if I'm given such an n-tuple of polynomials, let me call V pi something, say, reducible representation associated to pi, something in that isomorphism class. So then what one knows is that V pi is generated by an element little v pi, which satisfies the following relations. Okay? So xir plus on v pi equal to 0. This is something I wrote yesterday as n plus tensor CTT inverse of v pi. Then ki of v pi is equal to q to the degree of pi I v pi. So here pi is an n-tuple of polynomials, so let's call that pi 1 up to pi n. And so that's how ki transforms. And then pi of v pi, pi r of v pi, pi is defined that, is equal to pi I r of v pi. And this pi I r is equal, pi I is equal to summation pi I r. I'm just, yeah.
By the way, the number of the size of this tuple is the same as the rank.
Exactly.
Okay. That, I wasn't sure why that, I mean, in your discussion yesterday, I didn't know why n showed up, why the rank was showing up, per se. Because you initially showed an example of this where you just took one.
That was SL2.
That was the SL2 case.
That was the SL2 case. So you have these elements PIR defined one for each element of the.
Yeah.
These are the imaginary. So what I'm doing is picking a basis for the imaginary root space. So this corresponds to the imaginary root R delta.
Yeah, but that, no, I don't mean those p's.
Yeah.
I mean the tuple, the n tuple, which defines the representation, is pi 1 through pi n.
Yeah.
I mean, they have no relation with the pi's.
Yes. The pi's, PIR, acts on this vector v pi.
I see.
And the eigenvalues are given.
Okay.
So when you say the product, you mean sort of component wise?
Exactly, I mean the constant. Yeah. So pi is pi 1 up to pi n. So you think of this as, so you think of these polynomials as a monoid. So then the product pi prime is the product y. Okay. So what do you notice about the statement of this theorem? I've made many such statements before when I was talking about simple Lie algebras. So this statement looks like that, but it's missing something. What's it missing?
X sign minuses.
Yeah, no, yeah, okay. That should be there, I just forgot to put it. Okay, thank you. Now let's look for an intelligent answer. Are you feeling safe, Nathan? Okay. So there's still something missing in the way this is formulated. So what is the statement one makes for simple algebras? You say it's generated by an element V lambda which satisfies defining relations. Whose defining relations are, it's a Cartan, it's eigenvalue for the Cartan, n plus kills it, and this relation is there. What's missing over here is I haven't said these are the defining relations. I've just said it satisfies these relations. And the reason for that is one doesn't know defining relations in the quantum case, even for the finite dimensional. Okay. So you know, so let me make that comment, and then I'll tell you what this does. So even in the classical case, I think, so problem. What are the defining relations for the irreducible module? The answer would be a very good thesis. I don't know. So it's quite amazing. I mean, people have been studying this thing for a long time, and many of the simplest things are still not known, even though there are a million papers on the subject. Okay. So then, motivated by this problem and motivated by that theorem, let's define a module W pi
So,
yeah.
So, given set of pi,
Yeah.
you could put these relations and call it not quite this, maybe without those XIR,
Yeah.
and call it a
Weber
normal.
module. Correct. And then you're saying that the Weber module has a unique irreducible quotient, and that quotient is this V pi.
But we don't know.
You don't know generally.
That these are true, but what else?
Exactly. Right. So what I want to do is something intermediate to what you're saying. So let's define a module W pi, which has exactly those relations, which is generated by an element little w pi, which has exactly those as defining relations. Those as defining relations. So this is so this idea that you don't know defining relations for your irreducible module is something that happens in characteristic P. Because the module that has these as defining relations is what's called the wild module. And then the wild module has a unique irreducible quotient, but you don't know its defining relations. And so this is exactly the same thing that is happening here. So that motivated by that, we call W pi, so definition, W pi is called the wild module associated with pi. And to fully justify this, calling this the wild module, I want to state the following proposition. So much of all this has all been joint work with Presley. That was done sometime in 2000. W pi is finite dimensional. And so in some sense, W pi is the biggest module associated with this data. So the analogy with characteristic P is perfect. So it's finite dimensional and is biggest. So it has an obvious universal property module associated with this data. So these modules actually have a different geometric interpretation, which is given by Nakajima, who did it with queer varieties, and he calls them the standard. They're the exact same thing. So while modules are also while modules. So Nakajima doesn't give generators and relations for the while modules. He comes at it differently, but so are the same as standard modules for Nakajima. So this is one reason for calling these while modules. There is another reason, at least in the classical case. So what is the while module in the characteristic P case? You take the irreducible module in characteristic 0 and you go mod P. What is the analogy in the quantum case? You take an irreducible module in the quantum case, go mod Q equal to 1, and what you get then you want to call the while module. So the next justification, which is really what motivates the next week's lectures, really is that the limit of W pi as Q goes to 1 exists and is sort of the while module in the classical case. So again, it has nice universal properties, exactly like in characteristic in the loop case. So this I don't want to explain too much right now because well, I mean, so what you do is you show that it has, I explained lattices yesterday, so you show that this has a nice lattice, and then you can put Q equal to 1 and you get a module, and you know generators and relations for this module. Okay. So we'll look at that a bit more. All right. Okay. So now we have two families of modules which we will try to understand. So we have, so associated with my Drinfeld polynomials, I have my while module W pi, and I have my irreducible module D pi. I expect, at least for this, I know generators and relations, and experience tells me that maybe this is easier to understand than this one. In the characteristic P case, there's no work that needs to be done to understand this. You know, its character formula is given by Y character formula. So the question is, what does one mean by understand? So we want to understand these modules. And what one usually means by understanding is some kind of character theory. Right? So, i.e., want to understand characters.
In the classical case, there is these are the defining relations for that.
These are the defining relations. Sorry, for what?
For just the usual loop algebra.
Yeah.
So financial representations.
These are not the defining relations for the irreducible ones.
Oh, even in the classical case.
Even in the classical case, it should be. They're not enough.
Okay.
So this problem remains. I mean, as far as I know, this problem is also a problem in the classical case.
When you say classical, without the Q.
Without the Q, yeah. I don't know if it's, I mean, depending on the day, I would say I know how to do it, but today I don't know how to do it. But, I mean, I don't think it's written down anywhere, right? So, what the defining relations of the irreducible module are. So I don't know that. No.
So then this notion of L module and so on very much is there in the classical case.
Exactly. So yeah, so you see, so from my point of view, I don't like to think anymore in the quantum case because I hate its co-multiplication. I can't work with its co-multiplication. So I prefer to work at the classical case, and then I can lift information back very often to the quantum case. But of course, because then you don't, because you don't have this co-multiplication, it leads to other kinds of difficulties. Okay, so we want to understand the characters. What do we mean by characters? So one statement that I should have made and perhaps didn't make is, or maybe I did, I don't remember. So if you have UQG, and UQG has, so the irreducible finite dimensional representations of it are exactly like the finite. Sorry, you have a question?
Yeah. So when you say, maybe I'm just causing this guess right now. When Q goes to 1, what happens to pi itself?
The coefficients you put Q equal to 1. So you evaluate. I mean, of course, so if you're taking Q, limit Q going to 1, you can't think of Q as a complex number. You have to be then working over the over the ring of function. So you put that, so then your pi then will live in, if you're working in that situation, it will live here. Right? Now, these things won't always have a lattice, because if this polynomial is bad, it's obviously not going to have a lattice. So if you wanted to have a lattice, then you have to have this. Right? Because this is the lattice you are looking for. And then you just put Q equal to 1. See? Okay, so UQG, its irreducible finite dimensional representations are the same as that of UG. So we're staying away from Q being a root of unity, Q not a root of unity, because it's not true if Q is a root of unity, and also you know that finite dimensional so same. What does one mean by same? We've discussed this. It has a weight space decomposition, and the dimension of the weight spaces are the same as in the classical case. So its character is given by the wide character formula. Yeah? So then the finite dimensional representations are completely reducible. So I claim. Now I want to go to. So now I want to say that as a result of these observations, I've defined two kinds of characters for representations of UQL. So supposing V is a finite dimensional representation of UQ of LG, the preceding comment immediately gives not one but two definitions of character. And what are they? That's the first one. So the first one is just, it's a finite dimensional representation of UQ of LG that contains UQ of G, right? So you can just take the G character, which is the sum of the eigenspaces over the Ki. And what is another kind of G character that you could define? You could ask for multiplicities of the irreducible representation. Okay. So in principle, if you know one, you know the other, but in practice, you don't. Right? So you have the usual G character. So these are, let me write it. So it gives two definitions of characters. One is just that the character of V is equal to summation dimension V mu E mu. Okay. And the other, which I'll write as the G character of V, it's too annoying to write UQG, is equal to summation mu in P plus. Here I don't restrict, here mu is in P. Okay. The multiplicity of V mu in V character, G character of V mu. Okay, and V colon V mu equal to the dimension of form UQG V mu. So I just want to pick out the multiplicities of the irreducible representations. If I know this, I quite clearly will know this, because this is given by the Y character formula. This is a classical result. And of course, everybody loves to tell me that if you know this, you also know this, right? Because you know all the dimensions. And I always then want to know what are tensor product multiplicities, right? So supposing you take V lambda tensor V mu. The classical G module, right? You know the character of this module is given by the Y character formula. You know the character of this module is given by the Y character formula. The character of the product then is the product of the characters. And that tells me pretty damn little about what the multiplicity of V mu in this is. Right? So it's not enough to know this character, but it is certainly enough to know this character if you wanted to know that one. Okay. So these are like structure constants for this module. So there's a third notion of character over here, which is, so all these different notions of character are very useful because we know, in some ways, we know rather little about these representations. So the third notion of this character is something which is called the Q character, which is an unfortunate name. It should really be called the loop character, but it's now in the literature. So these elements HIR commute. But this is a definition that holds in the enveloping algebra. So you have a commuting family of endomorphisms on the finite dimensional vector space, because you have UQ and G module. Now if they were diagonalizable, then you could write it as a sum of eigenspaces. So what do you do if they're not diagonalizable? You can still write it as a direct sum of generalized eigenspaces. So we can write V as equal to direct sum V chi, and the sum over chi, and what is this chi? Chi is going to be a homomorphism from mu q of LH. So this is the algebra generated by HIR, I in I, R in Z, minus 0, 2. So chi varies over all algebra homomorphisms in this form. And then the Q character is equal to summation over chi, dimension of V chi, chi. You can do these definitions in the classical case as well. That's why it's not good to call it Q character. But it was originally done in the quantum case by Ed Frenkel and Reshetkin. So these Q characters were defined and studied initially by Frenkel, Reshetkin. And then further studied by Frenkel-Mukin. And then there's lots of work by Hernandez, which is very combinatorial. Okay, so, and there are other people who've done stuff on it.
Excuse me, before you erase that formula,
Yeah.
on the second one, on the second definition,
Yeah.
just to make sure that I've got it straight, you're taking V and you're viewing it now as a representation of G,
Right.
and it will decompose. You know it's a tensor product, so you decompose it. and
It's
then
not a tensor product. You don't know that it's a tensor product, but you know it's a finite dimensional G module.
Yeah, and it will be reducible, and then
Yes.
you're taking, I see, and then that V mu is actually not a eigenspace, but a representation.
Exactly. Eigenspaces are subscripts.
Yeah, okay.
Yeah. So this is actually an irreducible representation. So can I erase it now? Okay. And so these Q characters really lend themselves to lots of very interesting combinatorics. And
So I think UQLH is just a subalgebra of UQLG generated by
exactly. And you call it UQLH because these are like your Cartan elements. These are like okay. So there's this Q character, it's defined, and you know various things about it, but really no precious little. You can compute it in very few cases. And what would you really like? You would like something like a Y character formula, and that's a wonderful pipe dream, right? So no general theory in some sense. No general theory of Q characters. I mean, Nakajima would claim this in some case. There are some algorithms where you can compute them and so on, but there's no general theory of Q characters is really known. So by that I mean something pretty like the Y character formula.
Are they understood in the SL2 hat case?
Yeah, I'm going to say that. So they understood in the SL2 hat case. So let me just see. Yeah. So I've spent the last 40 minutes telling you that there's lots of literature and people still don't know very much, right? So how do people go about figuring out what to do, right? So the whole thing is too difficult, so what you do is you identify interesting families of modules. And you restrict your study to them. And how do you decide what's interesting? You look for input which comes from various places. So one of the inputs that came was from the work of Kirillov and Reshetikhin, for instance, and that came from their work on integrable systems. And so because of that, they could tell you that they were interested in some family of modules. And so then people decided, okay, let's just focus on that and see if we can do something. And then it turns out that mathematically, too, these Kirillov-Reshetikhin modules are very interesting, that they show up that in this Kashiwara crystal basis theory and so on, they're the most nicely behaved thing. So I think I'll take a break, and then I'll continue by telling you what some of these interesting families of modules are. And then that will be and that will include the SL2 example. So we'll start at 10:25. Okay, so I was going to tell you about all this input, but first let me continue to tell you what the basic difference from the classical case is and what the difficulties come from. So what played a very important role in the classical case was the evaluation representation, right? So the major role in the loop algebra case was played by the evaluation method. Right, so but that's how you had a representation of G, you pulled it back, and you could do nice things. Okay. In the quantum case, there does not exist an analog of this evaluation map. If G is not equal to SLN plus 1. It's not that one doesn't know how to define it, it's just not there. Okay. So, and this is the source of all difficulty. This is the problem of how to even construct examples of, concrete examples of representations. Okay. So how does one know that there doesn't exist an analog of this map? This is because almost at the beginning, Drinfeld gave an example in a slightly different context of an irreducible representation of G on which there was no way to put, that does not exist the structure of a UQ-LG module. So I should say UQG, structure of a UQ-LG. And actually the example that he gave was a very particular case of this family of examples that Kirillov and Reshetikhin described. Okay? However, for SLN plus 1, one does have the evaluation map. So let's first now, so as general rule in Lie theory, let's consider the case G equal to SL2.
So was this for a specific G?
So he gave an example of this for, so what he said was, well, okay, so his example would work for all algebras except A. So what he showed, so if G is not of type A, the adjoint representation is a fundamental representation. Okay? And he showed that the adjoint representation of G could not be made into a UQ-LG module if G was not of type SLN. It's a very simple example. You can do that. So let me give you the idea in the classical case. It won't be irreducible, but it will be indecomposable. Okay? So the exercise, supposing you take, so it's related to that. So supposing you take G and you give yourself the adjoint and you give yourself a copy of the trivial representation. Okay? And on this I'm going to put a structure of an LG module. Can I put a structure of LG? I better put a structure of a current algebra module. Just because I don't remember the formulas, okay? But so this is actually, so what Drinfeld was working with was exactly the quantum version of this. It's called the Yangian, okay? But never mind. So and now I'll define an action of x tensor t. So x tensor t power r acting on y and some complex number a, okay, is going to be 0. And then it's going to be delta R1 kappa xy. Kappa is a killing form. Okay. So if you look at this, this is an example of an indecomposable GT module. If you believe that this is a GT module, it's clear you can go from G to C, right? Because the killing form is non-degenerate. So if I take an element y over here, I just have to take my x. If I look at x tensor t, this will go to 0 kappa xy, which will be non-zero. So I can go from G to C. C is obviously a submodule because you don't see this at all, right? And then this is indecomposable. Yeah.
Is this for like r greater than 0, for r equal to 0? No?
No. What do you mean?
So whenever I act, I can never get anything from G?
Yeah, I'm evaluating
okay.
at 0 over there. Oh, sorry, you're right. No, you're right. This should be delta R0 x bracket y. Thank you. Yeah. So let me write that formula up here because that's fairly opaque now. So it's x tensor t power r acting on ya is equal to delta R0 x bracket y, comma, delta R1 kappa xy. Okay? So it's a simple exercise. This is an indecomposable GT module. And so in the quantum case, one can prove that these formulas don't quite work, but one can construct this module and show that it cannot be irreducible, that it is an irreducible module, and it can't be somehow made any smaller. So this is why there isn't an evaluation. So this is how one knows that there isn't an analog of the evaluation representation. Okay. I mean, this is not it's impossible to sort of convince you of this without going into much more detail about. So I'll try and explain as we go along why this is happening. But this example is the crux.
The T part is okay, but the T inverse part is wrong.
No, I think the T inverse part, it's just that I don't remember the formulas. But I think you could just do this for R and Z, and then you would do A to the R over here, okay? And here you would do R A to the R minus 1. Oh, well, A is bad notation. Yeah. So you would do this, and then here you would do, so you could, now let me just evaluate at 1. I don't want to evaluate at 0 because I'm doing T inverse, and so, and then this would be R kappa xy. I'm just taking derivative.
What I have difficulty in so it is also you're saying G is not.
Mm-hmm. I can, yeah. So you mean why am I restricting myself to GT?
Okay, no, so with all the T you are saying even in the GT inverse it's okay.
Yeah. So so I just wasn't prepared to write down this example, so now let me write down, now that I remember, let me write down the most general example, okay? So let me work with LG, and let me tell you what X tensor F acting on YA is, okay? This will be F of 1, X bracket Y, F prime at 1, take the derivative, kappa xy. No. A will not appear. This is supposed to be the trivial module. So if I take y to be 0, that will be 0. Okay. The formula that I wrote over there for the current algebra is evaluating at 0. This is, so you see, what's another way? I mean, this looks very bizarre, but it's actually built into your definition of the Kac-Moody algebra. Because what is your Kac-Moody algebra? You have 0 to CC to G hat, right? And what is this G hat? It was, forget the derivation. And then So if you sort of evaluate this g hat at 1, what you're going to get is this kind of thing. So I mean, yeah, it's really coming from that in that sense. But the critical thing is, why is this representation in the quantum case irreducible?
So, but you were saying that there does not exist the structure of the
Mm-hmm.
equation. So there is a quantum, slightly understanding. There is a quantum analog of this formula.
Of this formula.
Then that is giving a structure of the equation.
On a bigger space, it's not giving it to me on G. G is an irreducible representation for itself, and there is no way I can put a representation of LG on that space, UQ of LG on that space.
What you're saying, you show it by showing that this G, there is some C, this module cannot be made smaller.
Exactly.
I see. Okay, that's what you meant.
You remember we had these generators XIR plus or minus. They will go to more or less A plus or minus R XIR. No. Yeah. I think it will be just A to the R. Okay. There might be some powers of Q that I have to keep track of. Okay.
Maybe just xi.
Say that again?
It gets mapped to xir.
Oh, thank you. Yeah. Yeah. It's like saying that x tends to t power r goes to the r, x to the r. Yeah. There will be some powers of q over here, but anyway, we can look that up when we want to. Okay. So now we're in a good situation. We understand irreducible representations of this. Okay, so we pull it back. So let's look at Vn, where Vn is an irreducible representation of UQSL2. So I'm pulling back an irreducible representation, so I certainly continue to get an irreducible representation, right? So what is the question I should ask then? What do I know about irreducible representations? I know they're given by Drinfeld polynomials. So I should ask, this doesn't look like any Drinfeld polynomial over here, so I should ask, what is a Drinfeld polynomial that gives you this representation, right? In the classical case, what was the answer to this question? We didn't really answer it, but you did enough calculations, I think, in discussion yesterday. So in the classical case, so LG, and I did say this in some way, FA star Vn corresponds to the single polynomial 1 minus AU to the n. Right? So this is like the polynomial all has the same root. Polynomials has only one root, which occurs with multiplicity n. That was what the evaluation representation corresponded to. Quantum case. So UQ of LSL2. What are the Drinfeld polynomials corresponding to these irreducible representations? Okay. And so now here is something very pretty. If the Drinfeld polynomial will be 1 minus of the form 1 minus AQ to the n minus 1u into 1 minus AQ to the n minus 3u into 1 minus AQ to the minus n plus 1u. What do these numbers represent to you? They essentially represent the eigenvalues of h on your representation, or one less, right? So you have exactly the dimension of the representation number of roots. If you put q equal to 1, it becomes exactly that, right? But this thing also appears in when you're thinking in Hecke algebras, for instance, these kinds of strings, they give you, affine Hecke algebras, they give you irreducible representations. Okay, these kinds of strings. So, But you see, now it's becoming quite subtle to write down the Drinfeld polynomials, right? And now, so then the question is, so then when we were doing the classical case, we had a simple construction. We had a simple thing. We said that FA star Vn, tensor FA star, FB star Vm is irreducible if A is not equal to B. Right? This is something that we did. So if you took the thing at different points and you took tensor products, the tensor product was irreducible. But now you have, so if you take two things like this, then there's going to be some funnier interplay which gives you, it's probably not going to be as simple as this, just like the polynomial wasn't as simple. And so in fact, I want to tell you that tensor product, but I also want to answer, I guess, Jean's question earlier, which, was it your, somebody, about how does one know what the, or maybe Vishwanath asked me, how does one know what the Q characters are, right? So let's see how we would compute the Q characters here. So you know this evaluation map explicitly, correct? So that means you can calculate what PIR goes to explicitly, right? And then you're just pulling back. So that means you know the action of PIR on that entire space, right? And so if you do that calculation, if you even do it for V1, what you'll find is that the eigenvalues of PIR, so in this case there'll only be one thing since I'm doing SL2 on FA star Vn are given by rational functions in Q. So the top weight, so what is this looking like? Your top weight space is a polynomial. So that's looking like an integer, right? A positive integer, a dominant integral weight. And then the other things are differences of integers, right? They need not be positive, and those are looking like rational functions. So they are given by rational functions in Q. And they can be explicitly calculated. Okay. So, okay, so now I want to state my theorem on representations of theorem. So this was all in the same paper which we wrote on SL2, that any irreducible representation of UQ SL2 is isomorphic. So it looks formally very similar to a tensor product so F A1 star Vn1 tensor etc etc F AK star Vn N1 NK. And now instead of AI not equal to AJ, what I have to do is AI by AJ is, say that again? LSL to the AI. AI by AJ is not equal to Q raised to Ni plus Nj minus 2p plus or minus of that, where 0 less than or equal to p less than or equal to minimum of Ni Nj for all ij, for all 1 less than or equal to I not equal to j less than. So, supposing I took Q to be 1, what is this condition telling me? It's just telling me that AI is not equal to AJ, right? And if Q is different from 1, what is it telling me? How many values do I have, ratios do I have to exclude? I have to exclude this many ratios, yeah? What this should mean something to you. What does it, what do these things mean to you? What am I excluding really over here in some sense? So if you look at Vn tensor Vm, what do you know? Okay, let's do Vn tensor Vm. What do you know about it for SL2? You know it's Vn, n plus m, n plus m minus 2, right? And what this is telling me is that somehow I have to exclude something corresponding to each of these summands which appear in the Klebsch coordinate. Okay? So that is how one understands this. I'm sorry? No, what he did was, so let me say that. So, yeah. So how does one prove this theorem? You somehow prove it for a pair, and then you prove that once every pair is irreducible, then the whole tensor product is irreducible. And what Hernandez did was he showed that in general, if you took representations which were pairwise irreducible when you tensored then an arbitrary tensor product was irreducible. So this, yeah.
So if I look at this level of the Drinfeld polynomial,
Yeah.
am I just insisting that they just don't share any roots or something?
No, I'll show you. So you should draw a picture. So let's look at Ev. Oh, okay, so let's look at Ev A star V1, Ev tensor Ev AQ squared V1. Okay. Now, what is the Drinfeld polynomial of this? The Drinfeld let's represent the Drinfeld polynomial of this. It has only one root, right? So that's A. Okay. Maybe this example is too small. And if you look at the Drinfeld polynomial of this is AQ squared. So they're kind of adjacent. And actually, it's A inverse. So this example is. So it doesn't say that, but you see. What is this Drinfeld polynomial? What is a picture that you could draw with this Drinfeld polynomial? You could, so this is AQ to the n, AQ to the n minus 2, down to AQ to the minus n. So this is a picture. So you could draw the sequence of dots, each of which are q squared apart, correct? And what this condition, and then I could do the same thing with B. So I could do this, for instance. Yeah? B is, so B is another, so Ev B star Vm. Okay, so I could do this with B. So this condition is telling me, so now I have this string over here, and I have this string over here, and this condition is telling me that as long as these two together don't contain a bigger string, my tensor product is irreducible. That's exactly this condition. Whereas if they do, so if my A and B had been such that this looked like this, so this is here, and then so this part is Ev A, and now my B sort of starts here. Right? Then this is a big tensor, then I have a very large string. So my tensor product is reducible. I could have also started somewhere here, for instance, and then gone beyond it, and then again I'd have had a larger string. Okay? So my strings either have to be very far apart, more than q squared distance, very far apart, or they have to be, exactly, they have to not interact. That's what this condition is telling me, pictorially. Okay? So it's a very nice condition. So now what does this theorem tell me for about Q characters then? So over here I said that in an evaluation representation, the eigenvalues are given by rational functions. Okay? Characters are supposed to behave well. They're supposed to behave well with respect to direct sums. They should add up. With respect to tensor products, they should multiply. So what does this theorem tell me about Q characters of an arbitrary representation of UQLSL2? It says that the eigenvalues that appear are only rational functions because they have to be the products. Okay? And this is enough to say that for an arbitrary simple Lie algebra, so now supposing I take V and I look at UQ of LG and I want to know what its Q characters are, it's enough to know it in the SL2 case. And the SL2 case, this theorem tells you what all the Q characters are. So this is how one knows that the Q characters that appear are always rational functions. Okay, so they become more manageable. Right. So this theorem also gives you other kinds of information, or at least the proof of the theorem gave you other kinds of information. So for instance, I said that the R matrix doesn't give you isomorphisms in the quantum case. Okay? So in the course of this theorem, what one proves is, for instance, so you notice this plus or minus sign over here. So if you arrange your plus or minus correctly, so for instance, one can prove that, so let me just give you an example. So if you look at FA V1, tensor FA star VQ squared, okay, this is reducible. It doesn't satisfy this condition. It contains a unique irreducible sub. Okay. If I do the flip, so if I think of it in opposite co-multiplication, I meant 1. This has a unique irreducible quotient. Okay. So your R matrix doesn't so the thing is that in this situation, your R matrix it has parameters. It's called the trigonometric R matrix. Okay, and so the R matrix develops poles or singularities. So when it has a pole, you get a kernel. Okay, so the R matrix doesn't behave as nicely as it does for simple Lie algebras. It's not as rigid. So these two are clearly not isomorphic. You'll agree with that now, won't you? One has a unique irreducible sub, and
maybe you want a Q squared somewhere in the top.
Yeah, I want Q squared here, right? Oh yeah, I had my Q squared there. Yeah. Okay, it has a unique irreducible sub. So yeah, so unique irreducible sub, which will look like, so I should really write that, which will look like FAQ V2. And this will have a unique irreducible quotient, which will look like FAQ V2. Okay. And I claim that these two together should make it clear that this is not isomorphic to this. Because if this is FAQ V2, what is the quotient? How does V1 tensor V1 decompose? It decomposes as V2 plus C. So the quotient must be trivial. Whereas here the quotient is V2. So they cannot be isomorphic. Okay. Okay, so this theorem was proved 21 years ago. One still doesn't have any analog of this theorem for any other Lie algebra. Okay, so I think I'll stop at this point. I still have some stuff to say about this, so I'll maybe, if that's all right, I'll say some of it on Monday before going back to current algebra. But I think there are lots of problems in this area, so I think some of it might be interesting. And they're quite accessible by combinatorial methods, some of them at least. So, okay, so I'm done for today. Thank you very much.